thermal fluid sciences experts. This is ProReady Engineer.
Hello, this is Bassam Abdelnabi from ProReady Engineer. I'm excited to share a new video series featuring industry cases. If you like what you see, please consider liking and subscribing. Take care and talk to you soon.
Today, we are diving into a really high-stakes engineering case study. We're going to look at how one critical system, a system that was slow, inefficient, and honestly pretty dangerous, got completely transformed through some really smart engineering. It's a classic story of problem, solution, and some seriously powerful results. So let's start with a question. In a world like an aerospace test facility, where everything is happening under intense pressure, what is the actual cost of a single second? You might think, it's just a second, what's the big deal? But as you're about to see, that 1 second can be the razor-thin line between a perfect test run and a total disaster. For one major aerospace facility, that second was costing them big time. We're talking emergency trips, critical downtime, and some major safety risks. You know, every time this alert flashed, it was basically screaming that the system just couldn't keep up when things went wrong.
All right, so let's get right to the heart of the problem. This wasn't some minor bug or a simple glitch. No, this was a fundamental system failure. And it was all happening at a critical combustion test facility, where you can imagine the stakes are about as high as they get. So what did this failure look like on a daily basis? Well, for starters, the operators were constantly fighting with slow valve responses, which made any kind of precise control a total nightmare. Technicians were thus burning through precious test cell hours, doing constant manual recalibrations. But the really scary part? During an emergency, the fuel shutoff was so delayed that it would cause these dangerous spikes in flame temperature, putting hugely expensive equipment at risk.
So when the engineers finally got under the hood, they traced all that pain and frustration back to 3 core issues. Number 1, the old pneumatic system that controlled the valves was just way too slow for the job. 2, the valve materials themselves were wearing out super fast, which meant constant hands-on maintenance. And 3, this was a big one, a major design flaw where the emergency shutoff valves were just located too far away from where they were needed most.
Okay, so with problems this deep, you can't just slap a bandage on it, right? The solution had to be a complete re-engineering of the system to make it smarter, faster, and just fundamentally safer. And that called for a very deliberate 3-part engineering strategy.
And here is that plan of attack. First, rip out the old, slow pneumatic controls and upgrade to a modern, fast electronic system. Second, stop using the standard materials and bring in advanced, much more durable alloys for the valve components. And third, fix that critical safety flaw by moving those isolation valves right where they needed to be. This slide just says it all, doesn't it? On the left, you've got the old, clunky, sluggish pneumatic system. And on the right, the sleek, new electronic valves with their integrated digital feedback loop. It's like the difference between driving an old truck with loose steering and a brand new sports car with perfect, razor-sharp handling. And what was the immediate impact of that first change? A 35% faster response time. Now, that is not just a small improvement. For the operators trying to control these tests, that's an absolute game changer. The second fix was all about the materials. You see, the standard stainless steel parts in the old system would just get worn down and needed to be replaced all the time. The fix? Upgrading to stellite, which is an advanced alloy known for being incredibly tough and wear-resistant. And here's the key takeaway on that. Investing in better materials right at the start, well, it pays for itself over and over again with less maintenance, fewer part swaps, and most importantly, way less downtime. The system could just run longer and more reliably, period. Now for the third fix, and this one might be the most critical of all. The old design with the shutoff valve way down the pipe meant that in an emergency, all the fuel trapped in that pipe had to burn off. That's what caused those dangerous flame spikes. The new design was genius in its simplicity. They moved the valve right up next to the inlet, which minimized the amount of trapped gas to almost nothing. And the result of that one change? An instant fuel cutoff. No more lag. And that completely eliminated the risk of those crazy temperature surges. Emergency shutdowns became clean, immediate, and, most importantly, safe. So once all 3 of these fixes were in place, the system went from being in a constant state of red alert to being a reliable, high-performance green light machine. Let's take a look at the final results.
This table just lays it out so clearly. Let's just run down the list, shall we? Response time, 35% faster. Calibration, what used to be a constant manual chore, is now automatic.
Trim durability, thanks to that stellate alloy, saw a huge improvement. And emergency isolation went from being a delayed danger to an instant safety feature. I mean, look at that. It's a clean sweep. The new system won on every single metric.
And when you zoom out, you really see the whole picture. These weren't just 3 separate fixes. They were strategic moves that worked together to create a system that was just fundamentally better, slashing downtime, boosting safety, and giving operators the control they needed all at the same time. But, the biggest lesson from this whole project isn't really about valves or special alloys. It's about the core engineering philosophy that was behind every single decision they made.
And it all comes down to this one powerful idea: focusing on total life cycle economics rather than just the initial equipment price. See, they understood that the cheapest part off the shelf is almost never the most cost-effective solution in the long run. Real value is measured in reliability, safety, and uptime over the entire life of a system.
And that's really the question I want to leave you with. When you look at the systems that you depend on, were they just engineered to get up and running on day one? Or were they truly engineered to perform, to adapt, and to stay safe for their entire life cycle?
Because that long-term thinking, that focus on total life cycle economics and safety, at the end of the day, that is how you solve the toughest engineering challenges for good.